This video will discuss what is known as the empirical rule. The word empirical means to be discovered over a long period of time or to be looked at over a long period of time. And here's how this works now. If we know the mean and if we know the standard deviation of a particular distribution, and if we know that that distribution is symmetric, remember something is symmetric if the mean equals the median, or if you get, in particular, not only does it need to be symmetric, it needs to be unimodal, which means it has one peak. Well, a one peak symmetric distribution is called the normal curve, or if it's bell shaped. So if you have something that is normal or bell shaped, and you know the mean and you know the standard deviation, we can use what's known as the empirical rule. The empirical rule is also known as the 68, 95, 99.7% rule. These percentages correspond to the amount of data falling within 1, 2, and 3 standard deviations of the mean. And remember, a standard deviation is the average deviation away from the mean. So if we know a mean and a standard deviation, we can draw these normal curves. So the way this starts is we're going to draw normal curves. And a normal curve is a bell-shaped curve. And at the middle of every one of these normal curves will always lie the mean, which we call mu. So remember, mu is equal to the population mean. And it sits at the middle of every normal curve. So notice here you have the mean sitting here. And what we're going to be interested in now is, underneath every one of these curves, where the curve starts to drop, these are called inflection points. And an inflection point represents a standard deviation. So notice underneath this curve, there are 3 points to the right, 3 standard deviations to the right, and 3 standard deviations to the left, for a total of 6 standard deviations under this curve. Every normal curve has 6 standard deviations underneath it. And here's how this works now. We're interested in, here's 1 standard deviation away from the mean, and it's positive because it's above the mean. 2 standard deviations, 3 standard deviations. Here's -1 standard deviation, -2 standard deviations, -3 standard deviations. Well, if we know information, again, that the distribution is normal, and if we know that the mean of the curve, and if we know that the standard deviation of the curve, we can approximate the amount of data falling within these different curve areas. So for instance, inside of here, this is 1 standard deviation to the left and 1 standard deviation to the right. Within 1 standard deviation to the left and right is 68% of the data. And what that means is that, again, because it's the empirical rule and it's been looked at over time, we can look at this and see that anything that forms this shape has to have 68% of the data sitting in between 1 standard deviation. And what that means is that there's 1 standard deviation to the right and left is 68. We can cut this in half because this curve is symmetric. We can cut this in half and see that within 1 to the right is 34% of the data, and within 1 to the left is another 34% of the data, and it adds up to our 68%. Within 2 standard deviations of the mean, so now out here and out here, lies 95% of the data. And what that means now is that there is, from the mean to the -2 standard deviations is 47.5% of the data. And from here, and from the mean to the +2 standard deviations, also 47.5% of the data. So it also means that there is, and if you want to find how much is in each individual standard deviation, so sitting here and here, we would take 95 minus, well, we know together that this entire thing is 95%. We know that this part of it is only 68% though, so we do 95 minus 68%, and we get 27. But we know it's 27 split up amongst two tails, so we have to divide that by 2. So inside of here, we're going to get 13.5. So inside of here, we have 13.5 and 13.5. And again, that's because from this value here to here is 95%. But we already know that 68% of the value sits inside of here. So we take 95, subtract from 68, get 27, cut it in half, that gives us 13.5. Now, generally speaking, we're going to use this 95% cutoff as what we call usual. If something occurs 95% of the time, we're going to call it usual, which also means that if it's not occurring 95% of the time, which means it's occurring 5% of the time, we're going to call that unusual. So when you see something that occurs 5% or less of the time, it's considered to be unusual. And what that really means is that based on the normal curve, if it's more than 2 standard deviations away, we call this area unusual. Within 3 standard deviations of the mean lies 99.7% of the data. So you think about that, that's pretty much all of the data sitting within 3 standard deviations are sitting inside of here. So from here to here, from there to there is 99.7% of the data. So how much data doesn't sit inside of 3 standard deviations? And it tells us that only 0.3% of the data doesn't sit inside 3 standard deviations. And what that means is that if you try to calculate out here, then 0.3 doesn't sit inside. So that means this is, divide 0.3 in half, you get 0.15 and 0.15. And then if you look right here, it tells you that this part right here within the 3rd standard deviation, from here to here is 2.35. How are they getting that? Well, we know that from the red part here is 3 standard deviations. And we also know that from this part here, it's 95% of the data. So this time if we do 3 standard deviations is 99.7 minus 2 standard deviations is 95. That gives us 4.7%. And again, we have to divide this by 2 because it's sitting in both these tails right here and here. If you do 4.7 divided by 2, you get 2.35, which is how they're getting that. And it's vital that you understand and remember these numbers, or at least know how to get them. And we're going to call values that fall 3 standard deviations away from the mean outliers, which means that those values are so extreme and so unlikely to occur, they only occur at 0.15% of the time. Or, 0.15% of the time. So keep that in mind. That's a very extreme value. Remember, unusual is more than 95% or is less than 5% of the time. Unusual is less than 5%. So if it sits outside that 95% range, which is occurring less than 5%, is unusual. Extreme or outliers are going to be when they fall more than 3 standard deviations away. So let's do an example with this. And here's how we use it. This says the sample mean height of women in the U.S. ages 20 to 29 was 64.2 inches, with a sample standard deviation of 2.9 inches. Estimate the percent of women whose heights are between. And we're going to assume that these women this is a normal distribution, because this is an empirical rule problem. So we're going to assume it's normal. And here's what we're going to do first. We're going to draw a normal curve. And on this normal curve, we're going to label the mean, which was given to us. They tell us the mean is 64.2 inches. So we'll set the mean at the middle at 64.2. And we know the standard deviation is 2.9. Well, we said earlier that there's 6 deviations underneath this curve. 3 to the right, 1, 2, and 3. And 3 to the left, 1, 2, and 3. And we'll label those values now. So to the right, we're just going to add the 2.9 to 64.2. And we get the next value to the right is 67.1 plus another 2.9. We get 70 plus another 2.9. 72.9. So we go out to the right here with 3 standard deviations, starting at the mean, 64.2, then adding 2.9 and 2.9 and 2.9. Here's what we're going to get. To get the left-hand side, we just subtract 2.9. So 64.2 and we get 61.3 minus 2.9 again, 58.4 minus 2.9 again, and we get 55.5. So what I've done is, all I did was I set the mean at the middle of the curve, found 3 standard deviations to the right and 3 standard deviations to the left, because underneath this curve is always 6 standard deviations. And so what we're going to do now is use this information to answer this question. It says, estimate the percent of women whose heights are between 58.4 inches and 64.2 inches. Well, we can see that 58.4 inches is here and 64.2 inches is here at the mean. So we want to find this value. Well, we know that, and we can go back to our other slide a second ago that we looked at, where, look at this one more. Yeah, let's look at this one. In that area that we're looking at right now, let's clear this graph right here so you can see it. We can see that from the mean to the second standard deviation to the left is 34 plus 13.5%. Or that's equal to 47.5%. So 47.5% of the data sits inside of here. The next question says, women whose heights are greater than 58.4 inches. So greater than 58.4 starts here, and it moves this way now. And covers this entire part of the curve. Well, we look at this, we see that that's going to be 13.5 plus 34 plus 34 plus 13.5 plus 2.35 plus 0.015. Now we can add all these values up and get a number, but a much quicker way is to look at, well, we know the entire curve is equal to what number? What's this entire curve equal? If we're adding percents, this is 100%. And so we're adding all these numbers up back this way. What numbers are we not adding? Well, 2.35 and 0.15. And 2.35 plus 0.15 is equal to 2.5. So we're really not adding up 2.5% of the curve. So how can we find this by that method, or by using that? We know this is 100% minus 2.5, which is 97.5%. And if you add up 3.5 plus 34 plus 34 plus 13.5 plus 2.35 plus 0.15, you're also going to get 97.5%. The next question says, would it be unusual for a man to marry a woman that is 6 feet tall? Well, this curve is based in inches, so let's convert 6 feet to inches, and that'll be 72 inches. Well, would it be unusual for a man to marry a woman that is 6 feet tall? You look at this curve, we said unusual was anything that's not within 95%, so within 2 standard deviations. So unusual for this would be, this part is usual. Usual. That part is usual because that's the 2 standard deviation mark. And we see that 72 falls somewhere right here. Here's 72. So based off of that, would it be unusual? Yes. This falls more than 2 standard deviations away from the mean. So let's do one more example. This says the average IQ of all adults falls in an approximate normal distribution with a mean that is 100 and a standard deviation of 15. So because we have the word normal distribution, anytime you see these words, you should draw a curve, a normal curve. And set the mean at 100 and the standard deviation is 15. We go 15 to the right of 100, we get 115, another 15, 130, another 15, 145. Remember, that's 3 standard deviations to the right. To the left, we get 85, 70, and 55. And so that's 3 standard deviations to the left for a total of 6 sigma under the curve. Now, this says in a population of 1,000 people, how many would you expect to be labeled as genius, having an IQ greater than 130? So we come out here. These are the people we're going to label as genius. They have an IQ greater than 130. Well, we know that that is 2 standard deviations to the right, and greater than would be anything shaded this way. Well, we know that to the right of this should be, within here is from here to here is 2.35%, and then from here is 0.15%. If you add up 2.35 and 0.15%, you're going to get a total of 2.5% of the people. But it's 2.5% of the 1,000 people. And when you do that math, you're going to convert this to a decimal, so it's 0.025 of 1,000. And we get a total of 25 people. So out of 1,000 people, we can expect 25 of them to be genius. And this is how we really apply probabilities to real life. When we start to look at these standard deviations and you start to compare people, these standard deviations are really starting to become labels. So we're starting to label people as they move further out in each direction.